computer architecture communications. Let's take a look at what happens when we go further away the communication lines, further away from the central processing unit. There is a problem that arises, and first of all, of course, it becomes much slower because of Mr. Einstein and his speed of light that is limited. So actually what he says that information cannot propagate faster than the speed of light. And if we use a computer, it's exactly what we're doing. We're propagating information back and forth from the memory to the processor. That's why the things have to be as close as possible to the processor. Now, if we go further away, and we've seen last lecture in the hierarchy of the buses, that the things get further away from the processor and they get slower, and the further and further we go away, it will not only get slower, but we also get a problem with noise, and the noise will also force us to slow it down. The thing is that if you take a long piece of wire, for instance a track on a computer board, then this wire, it behaves as an antenna, and it will pick up all kinds of noise. Once it's inside the box and it is nicely shielded, it may be not such a big problem, and the antennas are anyway quite small because the distances are small. But once we start connecting external equipment, then this becomes a problem. The noise becomes a problem. So I will present to you two ways how this noise is avoided in communication, and I'm thinking especially about devices like USB, external hard disks and things like this. How do they avoid the noise problem? Now here's the first solution, which is a hardware problem. What we do, instead of taking one wire and communicating the data over this wire, we now take two wires, and this is called twisted pair because the two wires are twisted to be very close together and that they pick up actually the same noise. So what happens, in one wire we send the signal with a plus sign, and in the other wire we send the exact same signal but with a negative sign. And what we are doing then actually is, I will show it to you here, if on one wire we send the signal and it catches noise, I call here delta, and on the other wire we get minus the signal and it catches the same noise because it is so close together that the interference from outside, from the university, is more or less the same. If we now use a differential amplifier and amplify the differences between the two signals, you will get exactly only signal proportional to the original information signal, and the noise has been completely eradicated. Now, that is very nice. That is what we call twisted pair, and this is standard technology in communication over long distances, so you must understand that this is USB cables, this is Ethernet cables, and the likes, fire wires and whatever. They all use this twisted pair technology of using two wires for one signal. Of course it costs a little bit extra because you get an extra wire, but the advantage is you reduce the noise. Another way of reducing the noise is by adding redundant adding redundant information. That is to say, that is not information, because redundant information is information that you would know on basis of the other bits. It sounds maybe a little bit confusing, but let me explain to you here in what is called E81 Communication Convention, meaning you get 8 data bits, 1 parity bit and 1 stop bit. First of all, the stop bit is to synchronize to computers that they are actually getting the same packages, and they know basically when the packages stop and when they are starting. So you can for the moment forget this. This is just an electrical signal for synchronization. But what is interesting is this parity bit. This means a bit is added on top of the 8 data bits. You see here the 8 data bits, and in such a way that the total number of ones is, in this case, is 1, because we do even parity checking. So you see here 3 ones, 2 ones, so we need to put here a 1 to make it even parity. Now what happens if this signal somehow arrives as this? First of all, for us it's very easy to see. We can see here that this bit has gone wrong, but what if you only know this and you don't know this? Of course the receiver doesn't know the original message, and he doesn't know what went wrong or how it went wrong. He only gets this information. Did he already know this? Then of course the entire message would not contain information, as we know from the Shannon theory that we see here. Remember, I will talk about it later a little bit more. But now imagine that the computer on the other side receives this, and he doesn't know what the original message is. He starts counting 1, 2, 3, 4, 5 bits. Oh, that is not even. Something went wrong. I don't know what went wrong, but one of these bits, including the parity bit, went wrong. So what can I do now? Well, I can just ignore this and go on business as usual, or what I can do, I can ask the sender to send it again. And this last thing can be a little bit complicated. Imagine you're in a movie stream, and the thing of a stream is that the first pattern, the first package has not been arrived yet, while the others are already being sent. So that must mean that the receiver says like, oh, I want 2-3 seconds ago, I want that frame again because it went wrong. That is not very nice. So this kind of things is just for error checking, but not for error correction. So it just means something went wrong, and I don't know what to do, but maybe send it again, but something is wrong, so I will just ignore this. The much better way is what we say here, which is called Hamming 7.4, or forward error correction, it's also called. It's very often used in satellite communications and things like this. And it works as follows. Imagine you want to send 4 bits of data. I call them here D1, D2, D3, D4. Imagine that we want to send 1000. What do? We draw 3 circles, and then the intersection of the circles we place the data bits. And then we calculate what P1, P2, P3, what the parity bits should be, so that in every circle the parity is even. Let me show this here to you in an example. Imagine the data bits are 1, 0, 0, 0. Then to have even parity in this circle here, we need to put parity bit 1 here. In this circle we need to put the parity bit 1 here, then becomes 2, and in this circle we need to put the parity bit 0, because then this is 0, that's also even parity. So what do? We send the data bits 1, 0, 0, 0, and we send the parity bits 1, 1, 0. For a full pattern, 7.4, meaning 7 total, 4 data bits, 3 parity bits, 1, 0, 0, 0, 1, 1, 0. Now what happens if on the other side, imagine, we receive, instead of 1, 0, 0, 0, 1, 1, 0, we receive 1, 0, 0, 1, 1, 1, 0. The other side, the receiver, will do reverse engineering and will check in this circle, is this correct? Yes, this circle is correct. We have 2, parity 2, that's even. In this circle, no, we have here 3 bits that are 1. Meaning we have odd parity here. And this circle, hey, we also have odd parity. So not only do I know that something went wrong here and something went wrong here, and on top of that I know what went wrong, because I just look at the intersection of all the circles that had an error, that is circle B and circle C. The intersection cannot be part of A because A is correct, so the intersection of B and C and not A is here, this part which I marked in gray here. So that means that this one must have been wrong. So in this way not only can we detect errors, but we can actually eliminate them. And now the idea is that Mr. Shannon here, he said that in this way we can find a communication technique. So this is just Hamming, this is just a simple, well, relatively simple example. And Mr. Shannon says it is possible to have completely 100% errorless communication if you design your parity checking or your error correction protocol actually correct. And the thing is that, of course, this is very nice, mathematical genius, you call him, Mr. Shannon. On top of that, it is that the communications are becoming more reliable. The communications can be error correct. That means that if you're now watching digital television, you normally don't see a single error at all on your TV. The error bitrate must be becoming very bad before your television signal starts breaking down. And that is the advantage of digital communication and technologies like Mr. Hamming. And it is so advantageous that nowadays actually the same communication techniques of Hamming is being used in modern motherboards. Because then also you can actually increase the frequency of your motherboard, for instance your front side bus from 700 megahertz, maybe you can put it in 1.4 gigahertz, meaning the communication being faster. by using this kind of techniques. So that is to say that these communication techniques not only are for long distance telecommunications, but they're also for short distance inside your computer for advanced computers.